Jai Hind everyone. I am Deepak Narang, Assistant Professor in Electrical and Electronics Department of Ajay Kumar Garg Engineering College. The topic of my today discussion is time response analysis of second order system, which is very important topic of Unit 2 in this subject. So these are basically topics of my today's talk. Response of second order system. Basically we are going to derive the step response of second order system and the related time domain specification, which is delay time, rise time, peak overshoot, and settling time, and related numerical with this topic. Okay, before moving further, first of all, we should know what is time response of a system. Time response is nothing but how a system behaves with respect to time. Okay, it shows the time response. We can classify time response of a system into two parts. Say this is the time response. So we can classify as this is transient response and this is steady state response. So we are going to discuss both the responses of this second order system. Transient response basically shows the oscillatory behavior of the system, and the steady state response when these oscillatory behavior with the passage of time die out and a steady condition is achieved where output stays in a defined specific band, or you can say output stays near the our required desired output. We call it as steady state response. So starting with second order system, say this is our second order system. This is our second order system, unity feedback second order system. If we solve this, we can get its transfer function as ys over us is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. Why this is termed as second order system? Because it's the maximum power in the denominator of this transfer function is 2. That is why it is termed as second order system. So this is transfer function of this second order system, and this term is defined as damping ratio, and this term is defined as natural frequency of the system. So what is damping in the system? Damping basically is an opposition force to the oscillation which are produced in system, and the natural frequency basically the frequency with is intrinsic in any system and with which system shows oscillations. So if we increase the damping in the system, if this damping is high, then natural frequency keep on decreasing, and then we get a new frequency which is termed as omega d, which is termed as damped frequency. So we must have a basic knowledge of these terminologies while discussing the response of second order system. So to get the response, we are going to basically derive the value of Ct for this system. So first of all, we are considering the denominator term, or we can say the characteristic equation of this transfer function. Okay, so we are getting the, if we solve this quadratic equation by formula minus b plus minus b square minus 4ac upon 2a. Upon 2a, we get this value. We can say here this is our term b. This is a is over, a is 1, b is equal to 2 delta omega n, and c is equal to omega n square. Okay, so we get 2 roots minus delta omega n plus minus omega n delta square minus 1, which we can write as s is equal to minus delta omega n plus minus j, which is imaginary part, 1 minus delta square, and we call this omega n 1 minus delta square as damped frequency. This is damped frequency. Now, on the basis of this damping factor, we can divide our system as overdamped, underdamped, or critical damped. So we can see if delta is equal to 1, if we put delta is equal to 1, the roots of this equation will become s is equal to minus omega n, only this. So we are getting real roots and equal roots when delta is equal to 1. We can see there is no term of damping in this situation when we are having damping as 1, and system roots are completely function of natural frequency. So in such situation, the system may have only factor omega n if, say this, when there is no damping. Now considering this case, when damping is equal to 0, if we put damping as 0, okay, then we see we get roots as s is equal to plus minus j of omega n. It means the poles of system, if I draw here, the poles of system are lying on this imaginary axis, and when the system poles lies on this imaginary axis, the response is completely oscillatory. Okay, and the system will oscillate with its natural frequency omega n. Okay, and when the two roots are, when delta is equal to 1, this damping is greater than 1, we see we will get something omega n delta square minus 1, we will get real but unequal roots. So in such situation, this is case of over damping, and the roots will lie something here, and here system will have sluggish response. System will have sluggish response, and when delta is less than 1, we have roots as minus omega n plus minus j of some value. So we get complex conjugate roots, and the roots lie somewhat in this plane here, and when roots lie in this area, the system response is oscillatory, but these oscillations decay with time. So we can divide our transient response into two parts when system is, first of all, so depending upon the value of damping, we can define our system as critically damped when delta is equal to 1, it is underdamped when delta is less than 1, overdamped when delta is greater than 1, and when delta is equal to 0, system is said to be undamped system. If I draw it by its behavior, this is our standard output or reference output, we can say. This situation is when we are having delta less than 1, this response we get when delta is greater than 1. When damping is high, obviously it will make the response sluggish, and this response is when delta is equal to 1, and when no damping is there, okay, system will oscillate with the natural frequency. Now next is how to find the response of second order system. For this we will apply unit step signal to the system. As we know, our transfer function, which we have already defined, omega n square upon s square plus 2 zeta omega n s plus omega n square, and this is our unit step input. So we are considering all the three cases. First of all, when damping is 0, if we put damping as 0, so this becomes omega n square upon s square plus omega n square. This is equal to ys over rs, and as we know, rs is equal to, for this particular problem, is equal to 1 by s, and we get cs is equal to omega n square upon s square plus omega n square into 1 by s. After taking partial fraction and taking the inverse Laplace, we get time response as 1 minus cos omega nt into ut. Okay, so we can see here the time response is function of this omega n, and the system shows constant oscillation of fixed amplitude and frequency. So this case is known as undamped case. Next is step response when delta is taken as 1. This is situation where system is critically damped. When delta is equal to 1, if we put this value as 1, so this becomes equal to this s square plus 2 omega ns plus omega n square, and this is nothing but a perfect square of s plus omega n square. Just put the value of rs again, it becomes, again for rs is equal to 1 by s, and after taking partial fraction we get ct is equal to this. Now we can see here exponential term arises and the system response becomes like this. It rises slowly and move towards the reference output, and this situation is named as critical damped situation. Now the main part is when we consider system for under damping systems where delta is less than 1, and for this we have to make mathematical manipulation a little bit to take the Laplace inverse. First of all, write the overall transfer function which we are using since start, omega n square upon s square plus 2 delta omega ns plus omega n square. So to solve, to take its time response, we first are manipulating this denominator part. So we shall try to make its perfect square. To make its perfect square, we'll take the half of this value, that is delta omega n, and doing its square, and we'll add this term in this equation. So we are considering this denominator part which is characteristic of this system, and we are adding this delta omega n square and subtracting the same. So if we see, this become a perfect square s plus delta omega n whole square, and here taking the omega n square common, so this characteristic equation can be written as one minus del square. Now just put this equation in the transfer function here, and now take the step signal into account, and Cs becomes is equal to omega n square, this factor into this is multiplied by 1 by s, as we can see here. Now again take the partial fraction to solve this equation. We see partial fraction, to after solving partial fraction we get values as a is equal to 1, b is equal to -1, and c is equal to -2 delta omega n. Okay, so just by putting these values in this equation we get this part. So to take Laplace transform, we can see this pattern is resembling with the Laplace of either Laplace of sine or Laplace of cos. Here this is a upon s square plus a square, this is equal to s upon s square plus a square. And if we reduce this pattern into this form, we can easily take the Laplace inverse of this particular equation. To solve this further, we can split this part as delta omega n and delta omega n, and we are just doing the same. We are splitting this part into these two part. Okay, now here we can see this part we can write as omega d square. This is damped frequency, so we can see this is resembling with sine, with this form sine 80, but for this we need to have this part into numerator part. So we just multiply this factor into numerator and denominator, and we get this equation. Just and replace omega n square 1 minus delta by omega d, its damped frequency, and we get this equation. Now take the Laplace inverse 1 by s. The Laplace inverse of 1 by s is equal to 1, and for this is e raised to power minus delta omega nt cos omega dt. This will come as it is. For this, e raised to power minus omega nt and sine omega dt into ut. So this we have derived the complete time response we can make further manipulations in this time response. After taking this value, and this value common from this equation, we can write our equation as this. Now, if we consider this part as sin theta and this part as cos theta, so it makes formula of sin A plus B, which is sin A cos B plus cos A sin B. So we are doing the same, considering this part as sin theta and delta as cos theta. After substituting this value, this equation reduces to this form and we get this formula. We get the time response as a function of exponential term and sinusoidal term. This response is obtained when system is considered as underdamped system. So in such situation, when system is taken as underdamped system, we get the response like this: decaying oscillations with time, because here two factors are involved. One is exponentially, the response rises exponentially, and the sin omega t, so system is having oscillations as well with frequency omega d. This is damped frequency, not natural frequency. So here is this is standard time response of second order system. Now with this time response, some specifications are involved which are very important to discuss. These specifications are delay time, rise time, peak time, maximum peak overshoot, and settling time. Here, if this is delay time. Now what is delay time? Delay time is the time required by a system to reach 50% of its final value. If this is final value, so to reach its 50%, how much time is taken by system? This represents its delay time. And what is rise time? Rise time is taken in two respects. If system is overdamped, then the rise time will be the time taken by response to reach from 10 to 90% of its final value. This is rise time. This time is termed as rise time. But if the system is underdamped, then we say the time taken by response from its zero value to 100% of its final value is taken as rise time. Next is peak time. So when system shows its response, we can see some peaks are obtained. So the time taken by response to reach its first maximum peak, in what time the system is obtaining to its first maximum peak, is termed as its peak time. And what is maximum overshoot? The magnitude, this magnitude obtained by response, how far it has gone from its final value, this magnitude represents the maximum peak overshoot. Next is settling time. settling time is defined as the time after which oscillatory behavior dies out, or we can say the time at which system settles to a steady state condition. This is steady state condition. Response settles to a steady state value within a defined tolerance band. So this is termed as settling time. So this will be its settling time. So we are going to derive their values one by one. So first of all, we have already discussed this, the response to reach half of the final value, the response to rise from 0 to 100% of its final value. For this is for underdamped system. For overdamped, it is 10 to 90%. Okay, first of all, we are going to consider rise time. As you know, the time response of second order system was obtained as Ct is equal to 1 minus e raised to power minus delta omega nt upon 1 minus delta square into sine omega t plus theta. And we are considering this for underdamped system. We know for underdamped system, this is our rise time, and at this value, the response is, final response is 1. So if we are considering this as rise time at this value, this Ct will be equal to 1, because we are considering this response for unit step signal. That is why we have taken this value, final value, as 1. So 1 is cancelled out and this becomes equal to 0. So we are left with sine omega d2 is equal to theta. So we can say this angle part is equal to pi, and we get our rise time is equal to pi minus theta upon omega d. Okay, so this is the value of rise time. Next is equal to peak time. So if we consider peak time is this. To get the peak time, we see here the slope of time response at peak time dCTP, dCT upon dt at t is equal to Tp, this slope is equal to 0. So we are going to differentiate our time response with respect to time, and we get this equation. Okay. So at peak time, this complete differentiation or the value of slope will be equal to 0. So just taking again common factor from the equation, we get this part, and after solving, again making the formula sin a plus b for this equation, we get this value. By replacing this as sin theta, this as cos theta, we get this relationship, and this theta is cancelled out with this theta, and we get omega d Tp is equal to n pi, where n shows n is the number of overshoot. Okay, it will keep on changing with the overshoot value, or for maximum overshoot we take n is equal to 1 and we get peak time as equal to pi upon omega d. Just remember one thing, if we are considering this point, our Tp is equal to, and for this value n will be 1. If we are taking the time for this particular undershoot, here n is equal to 2. For this n is equal to 3. So accordingly n will get changed to on the basis of the peak value. Next is maximum peak overshoot. It defines the deviation of the response at peak time from the final value of the response, and this is maximum overshoot. We can say if this is the time response, this value shows the maximum overshoot. So we can see how it can be derived. If we know this complete magnitude and we subtract this magnitude from this, we will left with this magnitude, and this complete is time response at peak time, and this value is nothing but steady state output, which is this straight line. And if we normalize this, we generally take the peak overshoot as in terms of percentage, so we'll multiply it by 100. And since we are considering unit step signal, so for this percentage MPC TP minus 1 divided by 1, which is equal to CTP minus 1. So on the basis of this, we can define our maximum peak overshoot. CTPs, this is value of time response, just replacing TP as pi upon omega d. As we know, peak time value is, we have already defined peak time is equal to pi upon omega d. Just replacing TP with this value in this equation, we get this part. So omega is cancelled out with omega d. As we know, this part is equal to sine theta. So sine theta gets cancelled out with sine theta, and we are left with 1 plus e raised to power minus delta pi upon square root of 1 minus delta square, and this is equal to our CTP. Okay, now we are going to find out MP, and I already told that MP is equal to CTP minus C infinity over steady state value, and this is value is equal to 1. So if we take this is CTP and we are subtracting this value from this, and we are left with MP is equal to e raised to power, our MP becomes is equal to e raised to power minus delta pi upon 1 minus delta square. So we can see our peak overshoot is function of damping factor only. Peak overshoot is function of damping factor. Okay, so as damping increases, peak overshoot suppresses. So this is the percentage of peak overshoot in percentage term. Now next is settling time. This is the time required for the response to reach steady state and stay within the specified tolerance band around the final value. So if we are getting such response, so this response must stay in tolerance band, and this tolerance band is taken up to 2 to 5%. So we define our settling time for these two bands. For 5% tolerance band, settling time is equal to 3 upon delta omega n. For 2%, it is 4 upon delta omega n. Now let us consider numerical problem for a given system. We are given with this system k upon s plus 10 over, which is a unity feedback negative system. Okay, for this, if we take the transfer function of this system, this becomes k upon s square plus 10s plus k. Now what is given to us? find the value of k. This is supposed to find out. The system is having damping ratio as 0.5. So delta is given to us 0.5. Now what is our standard equation? Standard equation is s square plus 2 delta omega ns plus omega n square. If we compare these two equation, we observe that omega n square is equal to k. It means omega n is equal to square root of k. And secondly, we see 2 delta omega n is equal to 10. This implies 2 into 0.5, as delta is given 0.5, here we can see, and omega n is square root of k, this is equal to 10. So it means if we take the square both side, k is equal to 100. So first part we have obtained that value of k is coming out for this part is equal to 100. Next part is determine peak overshoot, this is peak time, maximum overshoot and settling time. So as we know, our peak time is equal to n pi upon omega d. So just put the value, n will be 1, 3.14 into 1 divided by omega n into 1 minus delta square. This is 3.14 divided by omega n is our omega n will be omega n is equal to, so omega n is equal to 10. 10 into 1 minus 0.5 whole square. After solving this, we can get peak time, which is comes out 0.363. Likewise, we can get the maximum overshoot. MP is e raised to power minus delta pi upon 1 minus square. So just put the value 0.5 into 3.14 divided by 1 minus. So this we get 0.163, or we can say 16.3% maximum overshoot. Likewise, we can also find the settling time. For settling time, just for 5%, for 2%, for 5%, this is delta. Just put the value, that is 3 upon 0.5 into 10. This is 0.6 second. Likewise, we can get for 2%, Ts is equal to 4 upon delta omega n. So this is how basically we solve the problems which are based upon second order system. So this was all about of this second order system, in which we discussed how to find time response of a system, the related parameters with second order time response, which is delay time, rise time, peak overshoot and settling time. So thank you. Jai Hind.